перелистнул 85-ю страницу своей истории, чтобы с новыми целями идти вперед вместе с вами.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings, and if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming festival of Nobel laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.
Nobel Fest.
События 2020 года. Пандемия, самоизоляция, локдауны. Да, но не только они. 2020 год – это плюс 15 тысяч жбановцев, новые лаборатории и кабинеты, новые возможности Smart University, создан автономный образовательный портал с собственной системой прокторинга. Увеличено количество услуг Smart Arsu, проведена неделя цифровизации. Достижения ученых. Учеными выиграны гранты на 160 миллионов тенге. Под руководством профессора Кванышбека Шункеева разработан учебник по физике для школьников Казахстана. Открыт диссертационный совет на соискание степени PhD по филологии. Защищена диссертация по математике. Успехи студентов. Волонтерские организации и школа волонтеров стали лучшими проектами области. Проведен международный студенческий семинар «Перспективы развития студенческого самоуправления в эпоху цифровизации». Участники стартап-академии выиграли гранты на свои проекты почти на 3 миллиона тенге. Международное признание. Университет стал соорганизатором международной конференции QS. Жбанов University впервые вошел в международный рейтинг QS University Ratings и ECA и занял 351 место среди лучших вузов. Год Абая. Имя и наследие Абая стало ближе тысячам казахстанцев. Проведено множество мероприятий и конкурсов. Опубликовано несколько научных трудов. Книга Абайтану передана во все школьные библиотеки области. И, конечно же, 2020 – это юбилейный год университета Жбанова. Проведено 85 благотворительных мероприятий. 503 человека награждены юбилейными медалями. 85 педагогов получили премии от областной профсоюзной организации работников образования и науки. Выпускники Актюбинской области стали обладателями 85 грантов имени Кудайбергена Жбанова. Зарегистрировано 85 патентов. Учеными факультетами передано в библиотеку по 85 книг. Студентами реализовано 85 стартап-проектов. В 2020 году Жбанов University перелистнул 85-ю страницу своей истории, чтобы с новыми целями идти вперед вместе с вами.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings. And if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming festival of Nobel laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.
Nobel Fest.
События 2020 года. Пандемия, самоизоляция, локдауны. Да, но не только они. 2020 год – это плюс 15 тысяч жбановцев, новые лаборатории и кабинеты, новые возможности Smart University, создан автономный образовательный портал с собственной системой прокторинга. Увеличено количество услуг Smart RSU, проведена неделя цифровизации. Достижения ученых. Учеными выиграны гранты на 160 миллионов тенге. Под руководством профессора Кванышбека Шункеева разработан учебник по физике для школьников Казахстана. Открыт диссертационный совет на соискание степени PhD по филологии. Защищена диссертация по математике. Успехи студентов. Волонтерские организации и школа волонтеров стали лучшими проектами области. Проведен международный студенческий семинар «Перспективы развития студенческого самоуправления в эпоху цифровизации». Участники стартап-академии выиграли гранты на свои проекты почти на 3 миллиона тенге. Международное признание. Университет стал соорганизатором международной конференции QS. Жбанов University впервые вошел в международный рейтинг QS University Rankings EECA и занял 351 место среди лучших вузов. Год Абая. Имя и наследие Абая стало ближе тысячам казахстанцев. Проведено множество мероприятий и конкурсов. Опубликовано несколько научных трудов. Книга Абайтану передана во все школьные библиотеки области. И, конечно же, 2020 – это юбилейный год университета Жбанова. Проведено 85 благотворительных мероприятий. 503 человека награждены юбилейными медалями. 85 педагогов получили премии от областной профсоюзной организации работников образования и науки. Выпускники Актюбинской области стали обладателями 85 грантов имени Кудайбергена Жбанова. Зарегистрировано 85 патентов. Учеными факультетами передано в библиотеку по 85 книг. Студентами реализовано 85 стартап-проектов. В 2020 году Жбанов University перелистнул 85-ю страницу своей истории, чтобы с новыми целями идти вперед вместе с вами.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings. And if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming Festival of Nobel Laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.
Nobel Fest.
So, welcome everybody. Welcome to this talk of today of this series of Nobel Laureate talks by the Inclusive Development Foundation. There's a series of very interesting talks that go on for the whole week, so I will encourage you to attend also the next ones until the 16th of April. And it's my great honor today to introduce to you Professor Kajita Takaaki, who is an expert on neutrinos. Every second, billions of neutrinos pass through our bodies, and we mostly don't notice. But somebody did take notice of this tiny particle and decided to learn more about it. And Professor Takaaki Kajita was involved in the Kamioka and then Super Kamioka experiments in Japan, which are amazing pieces of technology that allowed them to learn more about neutrinos and to discover that neutrinos have mass, that neutrinos oscillate between different types, which shows that they have mass. For this reason, Professor Kajita Takaaki received the Nobel Prize in Physics in 2015, and I should quote the reasons for the discovery of neutrino oscillations, which shows that neutrinos have mass, and also the breakthrough prize in fundamental physics, which is slightly more substantial and more modern version of these kind of recognition for amazing breakthroughs in fundamental physics. The amazing thing is that such a simple concept, a simple particle, and the idea of an oscillation could lead to such incredible, deeper understanding of the structure of the universe and fundamental physics, and the solution of some long-standing problems like the solar neutrino problem that has been there for decades, and that Professor Kajita's work helped to resolve. So I'm very honored and very happy to introduce to you Professor Kajita Takaaki, and I leave the floor to him. Thank you.
Well, thank you very much for the kind introduction. Well, okay, let me share my slides. Well, okay. Once again, thank you very much for the kind invitation to this fest. And today, I want to talk about the oscillating neutrinos and small neutrino mass. And now you see a photo in this slide. This is Super Kamioka, and we have been studying neutrinos with this detector. So today, I'm going to talk about the neutrino studies in Super Kamioka. And this is the outline. First, I have a brief introduction on neutrinos. Then I want to move on to the early days of the neutrino studies in Kamioka. That is the experiment called Kamioka. Then I want to move on to the discovery of neutrino oscillations in Super Kamioka. And before finishing this talk, I want to discuss the importance of small neutrino mass. And I'll summarize this talk. Okay, what are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. Neutrinos are something like electrons without electric charge. And in fact, this feature has a profound impact. Neutrinos can easily pass through even the Earth, but they can interact with the matter very rarely. And therefore, we can study neutrinos by observing this very rare neutrino interactions. Also, I want to mention that neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, I want to mention that physicists have been asking neutrinos rarely have no mass. And well, certainly in Super Kamioka, we had the same question and we studied neutrinos if neutrinos have mass. Now, this is the last page of the introduction. I'd like to briefly discuss how can we study neutrinos. Well, of course, we can never see neutrinos themselves. Instead, we can study neutrinos if a neutrino interact with a nucleus. Then in this case, a charged particle is emitted, and if this particle propagates in a medium, we have various ways to observe this particle. And for example, if this nucleus is a water nucleus, then charged particle propagate in the water. Then in this case, this particle emit photons. This is called Cherenkov photons. And therefore, we can observe these photons by photodetectors installed on the wall. So this way, we observe neutrino interactions. Okay, now I'd like to move on to the early days of our studies of neutrinos. Well, the whole history of the neutrino studies in Kamioka, by the way, Kamioka is the location of the experiment. Anyway, the history began almost 50 years ago. In the 70s, grand unified theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. This is a very long lifetime, but people thought, since this is a very important prediction, we should try to observe the proton decays. And therefore, several proton decay experiments began in the early 80s, and one of them was the Kamioka experiment. In the right side, I show the sketch of the Kamioka detector. It had about 16 meters in diameter and 16 meters in height, and it contained about 3,000 tons of very clean water. And well, certainly 3,000 tons of water contains many protons. Therefore, one of the protons may decay at that time. And if the decay happens, typically 2 to 3 particles are emitted. And these particles, while propagating in the water, emit Cherenkov photons, and therefore we observe these photons by the photodetectors installed on the detector wall. So this way, we wanted to observe proton decays. By the way, this detector was located 1,000 meters deep underground in order to minimize the background from the cosmic ray particles. Well, certainly we have to construct a detector. So in the spring of 1983, the experimental group came to Kamioka for the construction of the detector. And this photo was taken in the morning. And you can see a gentleman in the middle, in front, who is Professor Koshiba, who received Nobel Prize in Physics in 2002, based on his studies of astrophysical neutrinos in Kamioka. Anyway, these people worked in underground to construct the Kamioka detector. And this is one of the photos we took during the construction of the Kamioka experiment. You can see several plastic boats. And in fact, these boats were used to install the photodetectors onto the detector wall. Anyway, we worked in underground for several months, and the experiment started in July 1983. Of course, we wanted to observe proton decays. However, in all experiments, if there is a signal, there should be a background. And for Kamioka, the most serious background was the neutrino interactions. And these neutrinos were created by cosmic ray interactions in the atmosphere. cosmic ray particles, once enter into the atmosphere, interact with the air nucleus, and typically pions are created. Of course, pions are unstable, decay to a muon and neutrino, and muon is also unstable, decaying to an electron and other neutrinos. So these are the neutrinos created by cosmic ray interactions. And of course, most of these neutrinos simply pass through the Earth, but some of them interact in the Kamioka detector. And these are the most serious background to the search for proton decays. Now, let me discuss our story around 1986. At the time, we had still no evidence for proton decays. On the other hand, we had about 100 atmospheric neutrino background events. Therefore, we thought we have to better separate the proton decay signal and the neutrino backgrounds. And for this, we developed new software to improve the proton decay analysis. And of course, if you write a new software, you have to check this software as much as you can. So indeed, we did various tests of this software. And finally, as a test, the neutrino type was studied for the atmospheric neutrino events. And we found that the number of muon neutrino events was much fewer than expected. In the right side, I show an event pattern of the typical atmospheric muon neutrino interaction. So the new software told us this type of neutrino interaction was much fewer than expected. And since this was a test of the new software, we thought that it was very likely that there were some mistakes somewhere in the software. So we should find out the mistakes. Therefore, we started various studies to find out mistakes. And in fact, we worked quite hard to find mistakes. And indeed, we worked for about a year. But after about 1 year of studies, we were unable to find out any serious mistake. Therefore, we concluded that the muon neutrino deficit cannot be due to any major problem in the software. So we decided to publish our data. In fact, the paper we wrote at that time was quite simple. We simply reported the number of muon neutrino events observed, that was 85, and compared with the expectation, that was about 144. So clearly, data showed a significant deficit. Also, we counted the number of electron neutrino events. And for electron neutrinos, the observed data and the expectation agreed reasonably well. That's all we reported in that paper. Unfortunately, the world community was very much skeptical. So in that sense, we were depressed. But we thought our analysis is not a simple mistake. And we had no clear idea what was the cause of the deficit, but I was most excited with the data. I thought there must be something new indicated in the data. So I enjoyed to find out the cause of the deficit. And around that time, I changed my research from proton decay searches to neutrino studies. Well, certainly with the deficit alone, we are unable to find out the unique solution to the deficit. However, from the beginning, we thought that maybe neutrino oscillation was the cause of the deficit. Well, neutrino oscillation was predicted more than half a century ago by several theorists. They were Maki, Nakagawa, Sakata, and independently Pontecorvo. According to them, if neutrinos have mass, neutrinos change their type from one type to the other. For example, as indicated, as shown in this figure, if a muon neutrino is created in this point and begin to propagate to the right, then the probability that muon neutrino to remain muon neutrinos goes down. But if they continue to propagate, then the probability that muon neutrino to remain muon neutrino come back to unity. Then probability goes down again, come back to unity, and so on. And when the muon neutrino disappeared, tau neutrino is appearing. So this is the neutrino oscillations. And if this is happening, one can naturally explain the deficit of muon neutrinos. So we wanted to confirm if neutrino oscillation was the cause of the deficit. Of course, neutrino oscillation was one of the possible explanations for the deficit. Therefore, we wanted to separate the neutrino oscillation possibility and other possibilities. And for this, we thought this way. I mentioned that neutrinos were created by cosmic ray interactions in the atmosphere. Therefore, some of these neutrinos were created in the atmosphere above us, that is, say, 10 to 20 kilometers above us. And these neutrinos come to the detector after traveling 10 to 20 kilometers. Therefore, these neutrinos may not have enough time to oscillate because the flight length is so short. On the other hand, neutrinos are also created in the other side of the Earth. And these neutrinos propagate in the Earth before coming to this detector. Therefore, these neutrinos must propagate long distance, typically 10,000 kilometers. And therefore, these neutrinos may have enough time to oscillate. So if we think this way, we thought that we should observe the up versus down asymmetry of the atmospheric muon neutrino flux. Yes, we should try, but unfortunately, the Kamioka 3,000-ton detector was too small for this kind of studies. A much larger detector was necessary, and that was Super Kamioka. Okay, now I want to move on to the discovery of neutrino oscillations. Well, Super Kamioka is in fact a much larger version of the original Kamioka detector. It is about 40 meters in diameter and 40 meters in height. It contains about 50,000 tons of very clean water. And it is an international collaboration. We have about 200 collaborators from 10 countries. Well, this project was approved in 1991 by the Japanese government, and the construction period was for 5 years. And the last year, that was 95, was the installation of the photomultiplier tubes or photodetectors onto the detector wall. And at that stage, we came to underground Kamioka for the installation of the photodetectors. And this photo was taken during this kind of work. And you can see many people working. And in fact, about 70 to 80% of these people were physicists. So Super Kamioka and the collaborators worked in underground for about a year for the construction of the detector. And I think that construction work went well. And in fact, in January 96, we started filling pure water into the detector tank. And well, here I show the photo of the Super Kamioka and the detector taken in January 96. And you can, well, by the way, this photo was taken from the top of the detector, viewing inside. And you can see the water level. So around that time, to the Super Kamioka and the tank. And the experiment started in April 96. And we begin to observe atmospheric neutrino interactions. This is one of the observed events in Super Kamioka. Here you see many dots. And in fact, each dot represents the photomultiplier tube that received the photons. And the diameter, or maybe area of these dots represent the photon intensity. And also you see the color, and the color indicates the photon arrival timing. So we observe this kind of neutrino interactions every day, about 10 neutrino interactions in a day. And we formed a team to analyze these events. And we worked quite hard. In fact, in 2 years, we were able to report our first major result at the Neutrino conference. And here I show one of the slides we presented at the conference. By the way, more than 20 years ago, we didn't have PowerPoint. So we used plastic film to show the Super Kamioka and the data. Anyway, these data show the genius angle distributions for electron-neutrino interactions and mu-neutrino interactions. And the horizontal axis shows the neutrino arrival direction, and cosine theta 1 means downgoing neutrinos, -1 means upward going neutrinos. They came from the other side of the Earth. And these black circles with the error bars show the data, and this hatched histogram shows the Monte Carlo prediction without neutrino oscillations. And then you find for downgoing neutrinos, the data and the simulation agreed quite well. On the other hand, for the upward going neutrinos, the data showed almost a factor of 2 deficit compared with the expectation. And this can be, of course, very well explained if we assume neutrino oscillations. Neutrinos created in the other side of the Earth oscillate while propagating in the Earth, and therefore the probability that the muon neutrino to remain muon neutrino when they come to the super Kamioka and the detector is just 1/2. So this way, we were able to convince the world neutrino community that neutrinos oscillate. Of course, we reported this result at the neutrino conference, that is for experts on neutrinos. But something unexpected happened. The US President Clinton, gave a talk at MIT's 1998 commencement. And during his talk, he mentioned about the super Kamioka experiment. And here I copied the relevant part. And he said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. And of course, since he is the US president, he mentioned that in super Kamioka there are big US contributions. Then he came back and said, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So I think this kind of remark by the US president was really an honor for us. Okay, now I want to briefly discuss another discovery of neutrino oscillations, that is the solar neutrino oscillations. Of course, the sun generates energy by nuclear fusion processes, and during these processes, many neutrinos are generated. Therefore, physicists thought that if we observe solar neutrinos, that could be the evidence that sun generates energy by nuclear fusion processes. And therefore, about half a century ago, the pioneering home-stake solar neutrino experiment observed solar neutrinos for the first time. However, the event rate was about 1/3 of the prediction. And this problem was confirmed by the subsequent experiments in the 80s and 90s. And people in the community thought that maybe the solar neutrino deficit is due to neutrino oscillations. However, during the 20th century, we were unable to get the experimental answer to this problem. And the snow detector was the key player in discovering the solar neutrino oscillations. It is a 1,000-ton heavy water detector located 2 kilometers very deep underground. By using the heavy water, snow experiment can observe the electron-neutrino flux by this reaction. Nu-E interacting with deuteron producing E-PP. By observing this reaction, they can observe the Nu-E flux. Also, independently, they observe the total neutrino flux. By this reaction, neutrino plus deuteron going to neutrino plus proton plus neutron. So this is a measurement independent of the neutrino flavor, neutrino type. Then the result from this experiment is summarized here. If they observe the Nu-E flux, the observed flux was only about 1/3 of the expectation. But if they observe the total neutrino flux, the observed flux was just as expected. So clearly, this indicates that 2/3 of the flux is nu mu plus nu tau, and therefore, this missing solar neutrino problem was due to neutrino oscillations. By the way, Super Kamioka also contributed to understand this problem. Super Kamioka observed the solar neutrino flux by electron neutrinos by neutrino elastic scattering. Neutrino interact with an electron producing neutrino plus an electron. And this reaction is most sensitive to Nu-E, but also with a reduced cross-section, this reaction can study nu mu plus nu tau. And the observed data is shown here. And in fact, this data was just consistent with the SNO result. And this way, around 2001 to 2002, people were convinced that the solar neutrino deficit was due to neutrino oscillations. Now, I want to move on to the importance of small neutrino mass. Well, so far, I have discussed the discovery of nu mu to nu tau oscillations and the solar neutrino oscillations. And since then, various studies of neutrino oscillations were carried out. And now we understand the neutrino mass themselves quite well. And I'd like to compare the neutrino mass with the mass of other particles. Here, I plotted the mass of charged leptons. They are shown by red colors. And also the mass of quarks are shown by blue and green colors. Now, I want to overlay the neutrino mass. They are approximately here. Well, to be honest, we still have some uncertainties, but well, for this, I think it's okay. So with some assumptions, neutrino mass could be plotted here and here. And clearly, by looking at this figure, you notice that the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. So 10 orders of magnitude smaller. So neutrino mass is extremely small. And we believe this is the key to better understand elementary particles and the universe. Certainly, if we understand why neutrino mass is this small, we can better understand elementary particles. But also we think that the small neutrino mass could be the key to understand the universe. And for this, I'd like to explain a little bit. Here, I copied a photo of the far universe. You see many galaxies and stars. And we know that all these stars and galaxies are made of matter. We know there's no antimatter galaxy, no antimatter star. On the other hand, we know that our universe began with Big Bang. And in the Big Bang universe, the temperature was extremely high. And in the Big Bang universe, always particles and antiparticles were created simultaneously. So in the Big Bang universe, we expect that the number of particles and the antiparticles were equal. Then, with the universe cooled down, particles and the antiparticles meet and annihilate. Therefore, we naively expect in the present-day universe, there must be no matter particles, no antimatter particles remaining. But of course, matter particles remained, survived. Why? Well, we think we understand the mechanism. In the Big Bang universe, for example, the number of protons or matter particles were 1 billion plus 1. On the other hand, number of antimatter particles were 1 billion. They were almost equal. Then, with the universe cooled down, matter and antimatter particles meet and annihilate. Therefore, this one remained in the present-day universe. So this way, we can explain the matter in the universe now. Well, certainly 1 billion 1 is almost equal to 1 billion, but not exactly. Therefore, we have to explain why there was extra 1 in the number of matter particles in the Big Bang. And in fact, we do not know the reason, but many people think that neutrinos with very small mass might be the key to understand this big mystery of the matter in the universe. Well, okay, so many people think this way. If so, we have to check if this idea is correct. And for this, we'd like to know if neutrinos are related to the origin of the matter in the universe. And for this, we'd like to observe if neutrino oscillations of neutrinos and those of antineutrinos are different. Unfortunately, the present long baseline experiments are not powerful enough. Therefore, we need the next generation long baseline experiments with much higher performance neutrino detectors. And I think we are fortunate. There are 2 projects going on. One is the DUNE project in the United States. In this project, neutrinos are created in Fermilab, and they are detected by the DUNE detector that is 1,300 kilometers away from Fermilab. Another project is the Hyper-Kamioka. Neutrinos are created in JPAC, and they are detected by Hyper-Kamioka. And from now on, since I'm somehow involved in the Hyper-Kamioka project, I'd like to briefly discuss the Hyper-Kamioka project. It is a long baseline experiment between JPAC and Hyper-Kamioka. The baseline length is about 300 kilometers. In this project, we are going to construct the next generation experiment detector, Hyper-Kamioka. it will be a 190 kiloton large water detector. It will have about 70 meters in diameter and 70 meters in height. Furthermore, we are going to improve the accelerator part. And JPAC is the accelerator to produce neutrinos. And at this moment, this accelerator has the beam power of 0.5 megawatt, but we are going to improve the beam power to 1.3 megawatt. And therefore, by combining this detector improvement and the accelerator improvement, the event rate of the neutrino interaction will be improved by a factor of 22 compared with the present T2K experiment. By the way, this is located in Japan, but this is truly an international collaboration. We have more than 400 members from 19 countries. And this is the Kamioka construction schedule. The project was approved about 1 year ago. Then we are now in the construction phase. We are now beginning of the fiscal year 2021, and the tunnel construction is going to start soon. And the photomultiplier tubes for the Kamioka detector is already in the production phase. Also, the JPAC accelerator is going to be upgraded, and we'd like to begin the experiment in 2027. And I'd like to briefly show you the status of the Kamioka. The left photo shows the Kamioka site. Well, at the site, we have the geological survey, and the right upper photo shows the photomultiplier tubes for Kamioka. Or these tubes are, some of these tubes are already delivered to the site. And this is the photo of the entrance yard. And in fact, from now on, we begin the excavation of the entrance or tunnel to the Kamioka site. Okay, let me summarize. Neutrinos are very interesting particles. Neutrino oscillations and therefore small neutrino mass were discovered by Super Kamioka in 1998. And small neutrino mass is very important for better understanding of elementary particles. And small neutrino mass might also be the key to understand the fundamental questions of the universe. And we'd like to continue contributing to neutrino physics and astrophysics with the next generation experiment, Kamioka. Okay, that's all. Thank you very much for your attention.
Thank you very much, Professor Kajita. And there's a few questions here in the chat, and a lot of our listeners are young people and potentially future scientists. And so they would like to know a little bit about your experience and your path. So I don't know if you want me to read the questions out loud or if you want to read them yourself. What would you prefer?
Well, okay, I can read and I'll answer.
Thank you.
Okay, the first question is, what inspired you for so many years to work on such an undiscovered topic? Well, okay, thank you very much for this question. Certainly, well, I think I was very lucky because I accidentally, unexpectedly discovered the problem. And I thought it's not a good idea not to think about this problem. So I decided to understand what's going on with the neutrinos. And so this was the motivation for continuing the neutrinos. Second, who did help you to realize and achieve the experimental goals? Okay, thank you for this question. Well, certainly, without my colleagues, it was simply not possible to come to discover neutrino oscillations. Certainly, I have many important key persons. For example, one of them is Professor Koshiba, who was the leader of the Kamioka experiment, and who also proposed super Kamioka for the first time. And also, he helped me a lot during the Kamioka experiment. I said Kamioka discovered the deficit of atmospheric neutrinos. However, after our paper, the world community was not very positive, and therefore I didn't have any much support from other colleagues. But Professor Koshiba always encouraged me to continue the study of the atmospheric neutrinos. Certainly, Professor Koshiba was a very important person for me. The third question is how it did help Japan or Japanese companies. Okay, thank you. Well, in fact, I think, well, Super Kamioka or Kamioka was actually helped by the Japanese companies. In Kamioka and Super Kamioka, we use 50 centimeter diameter photomultiplier tubes. But, well, when I was an undergraduate student, the typical size of the photomultiplier tube was, say, 5 centimeters. And this company, Japanese company, agreed to develop a large size photomultiplier tube. And because of the successful development, Kamioka and Super Kamioka was successful. Therefore, we were helped by this company. Now I want to move on to the second person. I'm going to join of university's questions and ask Professor Kajita the following. How did you feel when you received your award? Well, okay, thank you very much. Well, certainly it was, of course, an honor. But also at the same time, I thought I was extremely lucky. I had good advisor, good colleague, and good project. And finally, the nature was very kind to us. The neutrino oscillation parameter was just right for us to discover neutrino oscillations. Okay, then second, what does this recognition mean for you personally and for your country community? Okay, thank you. Well, certainly, personally, this is really a great honor. and for the Japanese country, I hope that this recognition help the Japanese people to recognize the importance of the basic science. Now, Japan has more weight on the innovation rather than the basic science. So I hope that people realize the importance of the basic science. I want to move on. What makes you wake up every morning and keep working hard in your scientific field? What drives you? Well, certainly, before the discovery of neutrino oscillations, scientific interest was the whole of my motivation. As I said, I was most excited with the deficit, and I really wanted to know what was the cause of the deficit. So only science made me work hard. Then I want to move on. How long is it required to approve the project? Okay, thank you very much for this question. In fact, already in 1983, Professor Koshiba proposed the initial idea for super Kamioka. Then we did many works, and finally in 91, the super Kamioka project was approved. So from the initial idea to the approval, it was about 8 years. And what was the source of funding to implement the project? Okay. Well, in Japan, there's funding that support the large infrastructure for the scientific research. And super Kamioka was included in one of them. How international partners can join the project? Okay, well, certainly, when we started the collaboration with our US colleagues, they contacted us when we started the construction, and we decided that Japanese group will have the responsibility in this part, and the US group will have the responsibility in other part. So that way, we decided to collaborate. And now, since the detector is already existing, people typically join to the super Kamioka experiment, trying to contribute by the data analysis. Okay, I want to move on. Can researchers or universities from Kazakhstan join JPAC project, and what are the requirements? Okay, thank you. The answer is yes, they can. You can join. About the requirements, I'm very sorry, but I don't know. There must be some requirements, but I don't know. Then next question. Why or what influenced your decision to pursue science? Okay, thank you very much for this question. Well, I decided because I was interested in understanding the universe or elementary particles, that's all. Well, certainly I was young. Okay, move on. what breakthrough discoveries in science we should expect in the next 10 years? Thank you very much for this question. Certainly, I discussed at the end of my talk a possibility to study oscillation of neutrinos and oscillation of antineutrinos. And if we observe the difference between them, that could be a very important discovery. Other than that, I hope that people discover dark matter particles, but I don't know.
Yes, I believe this was the last. So, and we're perfectly on time. It's exactly 12. And thank you very much for the enlightening answers and very inspiring answers. And I think we can see that it's a combination, such brilliant success. It's a combination of determination, good support, good mentors, a good problem to solve. And as you said, nature also has to be kind to you in order to give you a problem that you can solve, which not always happens. And was very, very interesting, was very, very inspiring for all of us. So I would like, on behalf of everybody, to thank you once again. And I wish you best of luck also for the future neutrino experiments.
Thank you. Thank you very much.
События 2020 года. Пандемия, самоизоляция, локдауны. Да, но не только они. 2020 год – это плюс 15 тысяч шибановцев, новые лаборатории и кабинеты, новые возможности Smart University, создан автономный образовательный портал с собственной системой прокторинга. Увеличено количество услуг Smart Arsu, проведена неделя цифровизации. Достижения ученых. Учеными выиграны гранты на 160 миллионов тенге. Под руководством профессора Кванышбека Шункеева разработан учебник по физике для школьников Казахстана. Открыт диссертационный совет на соискание степени PhD по филологии. Защищена диссертация по математике. Успехи студентов. Волонтерские организации и школа волонтеров стали лучшими проектами области. Проведен международный студенческий семинар «Перспективы развития студенческого самоуправления в эпоху цифровизации». Участники стартап-академии выиграли гранты на свои проекты почти на 3 миллиона тенге. Международное признание. Университет стал соорганизатором международной конференции QS. Жбанов University впервые вошел в международный рейтинг QS University Rankings и ECA и занял 351 место среди лучших вузов. Год Абая. Имя и наследие Абая стало ближе тысячам казахстанцев. Проведено множество мероприятий и конкурсов. Опубликовано несколько научных трудов. Книга Абайтану передана во все школьные библиотеки области. И, конечно же, 2020 – это юбилейный год университета Жбанова. Проведено 85 благотворительных мероприятий. 503 человека награждены юбилейными медалями. 85 педагогов получили премии от областной профсоюзной организации работников образования и науки. Выпускники Актюбинской области стали обладателями 85 грантов имени Кудайбергена Жбанова. Зарегистрировано 85 патентов. Учеными факультетами передано в библиотеку по 85 книг. Студентами реализовано 85 стартап-проектов. В 2020 году Жбанов University перелистнул 85-ю страницу своей истории, чтобы с новыми целями идти вперед вместе с вами.